All right, so for the second section of 1-2, you're going to have to bear with me a little bit because we have a lot to go over. So it's going to take a little bit of time. Make sure that if you need to pause the video to write down, get anything in your notes, that you do so. And if you have any questions, make sure you write those down. But as you can see here, we've got a lot of things that we need to talk about today. So I'm going to talk about continuity. We're going to talk about increasing and decreasing functions. We're going to talk about if a function is bounded or not. We're going to talk about local and absolute extrema, symmetry, asymptotes, and end behavior as well. So let's go ahead and start talking about if a graph is continuous or not. So when you have a continuous graph, that means that there are no breaks, there are no holes in it. And so the graph that I have shown here over on the left is a continuous graph because, as you can see, it is one line that is being drawn, and that's exactly what a continuous graph is. If you have removable discontinuity, then that means that you are putting a hole in the graph, which will show you kind of what that looks like. But that's saying that you have a continuous line, but then all of a sudden there's one spot in it where it's not there. If you have jump discontinuity, then that means that you have two lines that are going off of each other. This often happens with our piecewise functions. And it's starting on one line, and then all of a sudden it jumps to another line. And then you have infinite discontinuity when you have asymptotes that are being involved, where you have two lines where there's not necessarily a jump, where there's a point. We'll be talking about asymptotes to go along with this. So here's a graph that is discontinuous, or that's not continuous. And we can see this because there's two separate lines that are being drawn. And what it's having here is we have the infinite discontinuity going on here. And we have this invisible line that if I draw in here, where these two graphs are discontinuous, okay? And where that's existing here is when x is equal to 2. Now, if you look over here at the function that goes with this graph, hopefully you can see why this graph is not continuous at that point. And you see it right here in your denominator. And your denominator right there is x minus 2. Well, if I put 2 into that function, 2 minus 2, oops, 2 minus 2 is equal to 0. And we can never divide a fraction by 0. So what's happening here is that our graph is breaking off at that point, and we have this line that's being drawn here of where these two graphs, where no value of y exists. If I look at the next graph here, now this one looks like it's a continuous line, but actually it's not. There's actually a hole sitting right here at x equals 2. And you'll have to remember kind of how rational functions worked in Algebra 2, but we'll be talking more about those in later chapters. But this hole right here exists because if I look at this function here, it's graphed as a straight line. But the reason that it's graphed as a straight line is because if you remember about factoring out polynomials, so x minus 2 and x plus 2, when you simplify rational functions, if you have a common factor in your numerator and denominator, they cancel each other out, leaving us here with h of x equals x plus 2, which is a linear equation with a y-intercept at 2 and a slope of 1. So that's how we get this line. Now, if you go back to the original function, being x squared minus 4 divided by x minus 2, we have a problem because x cannot equal negative 2, or it can't equal positive 2, because if it did, you would end up with 0 in their denominator, and so that's why we have that hole that's in the middle of our graph. Now, as we start talking about points of discontinuity, then we start talking about asymptotes. And what asymptotes are they are kind of like invisible vertical and horizontal lines that a graph approaches but never necessarily touches or crosses that line. And what I have here is I have a function that actually has 3 asymptotes. It has 2 vertical asymptotes and it has 1 horizontal asymptote. Now the two vertical asymptotes are drawn in here at, it looks like we are at -2 and at +2. And the reason for that is because when I look at the denominator of my function, if I put in a +2 or a -2 into the function, I get a denominator of 0, which cannot happen. And so there's where those asymptotes are. Now the horizontal asymptote that's drawn in here, we'll be getting into that later. And what we have here is this horizontal asymptote is actually going to be going to, if I look at this right, -2 is where that horizontal asymptote is. And we'll be talking about what those are once we get into rational functions once again. But you should be able to look at a function and or a graph of a function and be able to identify the asymptotes just by looking at it. Now, when I look at this one here, hopefully you can clearly see with this function that we have clearly two vertical asymptotes that are that we can see at -1 and at +2. And what there also is there is a horizontal asymptote that we can work with as well. And the horizontal asymptote is actually right along your x-axis. And you might be saying, but how can that be a asymptote if right in the middle here, if it crosses through there? Well, just so you're aware that horizontal asymptotes can be crossed over. What we're going to be looking at with horizontal asymptotes is more so the end behavior that we'll talk about in a minute, and it's telling us what's happening as x gets very large or x gets very small. So with this graph here, like the last one, we have three asymptotes. We have two vertical and we have one horizontal. Next, I want to get into increasing and decreasing parts of a function. When you're talking about when a function is increasing on a given interval, it's talking about taking 2 points and where the slope between those 2 points is positive. So when you have a graph that's going uphill from left to right, it's an increasing function. If your function is going downhill from one point to another point, from left to right, and you have a negative slope, then you're talking about where your function is decreasing. If your function is a straight horizontal line where you have a slope of 0, then you're talking about a constant function. So I'm going to go to my next graph here, which I'm going to change one thing real quick, just so there we go. And with this function that I have here, I have a increasing part to it, I have a decreasing part, and I have a constant function. And so let's start out with the decreasing part. Our function, where it's going downhill, is from right in here. And it's going downhill from this value of x to here. So 1, 2, 3, 4, 5, 6, 7, 8. So from -8 to -5 is where our graph is decreasing. So we are decreasing for when x is between the interval where it's greater than or equal to -8 and where it's less than or equal to -5. And that's where we are decreasing. The next part of our graph here is remaining constant. So it's staying the same. And as we look at here, we have this horizontal line that's being drawn, and that's where we're going to have a constant graph. And our graph is constant as we go for when x is going from -5 to where it's going to +1. So when x is greater than or equal to -5 and less than or equal to +1, we're talking about a constant graph here. And then we have the last and final part to our graph here, which is increasing because we have a positive slope. And it's starting at +1, but because there is an arrow to it, it's going on forever. So this is saying that we are increasing, and we are increasing for when x is greater than or equal to +1. And that's where it's going to be increasing. It's going to increase for the rest of this entire graph that's here. Next, we're going to talk about when a graph has bounds to it, so if it's bounded or if it's not. And if you kind of look at these graphs, it might start to make sense. And when a graph is bounded, all it's saying is that it has a minimum and it has a maximum. So when you're talking about being bounded below, that means that your graph does not have a maximum, because this graph is going to go towards positive infinity for your maximum here, but it does have a minimum value, and so that would mean it's bounded below. If you do not have a minimum, but you have a maximum, that's saying that it's bounded above. If your graph does not go on forever and ever and ever, and you have a maximum and a minimum, then that's saying that it's bounded, and it would be bounded both above and below. When you have a graph here with no minimum and no maximum, then this graph here would not be bounded. And so just by looking at those examples, hopefully you can kind of see if a graph is bounded or not. Talking about if a graph is bounded or not, we're talking about having minimums or maximums. And we want to talk about having minimums and maximums as well as local and absolute extrema. So local maximums we will say as well. And what that's saying is you can still have a maximum if you have a graph that is not bounded above. You can still talk about a maximum. For example, right here's a graph that I have drawn out. And because this graph goes on forever and ever towards positive infinity for our y values, we do not have an overall maximum value. But we do have what's called a local maximum. And that local maximum, or absolute maximum too, as it can be said here, is going to be this value of 1.32. And that's just saying that we have a maximum other than, or we have a local maximum, which is not the overall. With this problem here, we have a minimum and we have a local minimum. Our minimum is going to be the lowest possible value, which is negative 24.06, where we have a local minimum of negative 1.77. So both of those are minimums. We have our overall minimum, and then we have our local minimum that's being used as well. So when I think about this, I like to think about our local minimums, our absolute minimum extrema. Those are all of our valleys. And when we talk about local maximums or absolute maximum extrema, we're talking about all the hills that go on with a graph. Next, I want to talk about symmetry, and the first one is when we have y-axis symmetry. Y-axis symmetry is if I draw a line down the y-axis, if that graph is the same on both sides. And what we do is, if a function does have y-axis symmetry, we say that it is an even function. By being an even function here, as I have here, it says f of x equals f of negative x. Well, here I have the function of y equals x squared. And if I were to go ahead and say that f of positive 2, so 2 squared gives me 4. And if I take f of negative 2, I get negative 2 squared, which also gives me 4. So here the fact that f of 2 equals f of negative 2, this is telling me here that I have y-axis symmetry. And overall, this is going to tell me that I have an even function. If we have x-axis symmetry, which it'll come up every once in a while, but the only thing is with x-axis symmetry is you have to realize that's not a function, because it does not pass the vertical line test. So we will talk about taking functions like this and restricting the domain to make them a function, but from here, with your x-axis symmetry, this is saying that your x values stay the same, but your y coordinates are going to be the opposites of each other, and this is not going to be a function. The other type of symmetry that we're going to look at is rotation symmetry, which means if you rotate a graph 180 degrees, you end up with the exact same graph. And what we do is we end up with that with the cubic function, so y is equal to x to the third. And this ends up being what we call an odd function if it has rotation symmetry. So notice that I have f of negative x equals negative f of x. So let me go ahead and just say, okay, if we take f of negative 2. So if I take negative 2 to the third power, I'm going to end up with negative 8. And now if I take that same value, if I take negative f of 2, I end up with negative of 2 to the third, which gives me negative 8. So here this is saying that f of negative 2 is equal to negative f of 2. And this tells me here that I do have rotation symmetry, which means that I have an odd function. And again, rotation symmetry means that if I rotate this graph, if I can show you, we'll kind of do this. If I rotate this graph 180 degrees, notice that it's the exact same graph that we started with. And the last thing that we're going to cover today is end behavior. And what end behavior is doing is it's ultimately talking about limits. And limits become very, very important once you get into calculus. And we'll talk about them a little bit here. We'll be doing a limit section later on. But what we're just going to do now here is just look at what's happening. What is happening to the value of y as the value of x gets very large or as the value of x gets really small? What do I mean by that? Okay, if I look at the x values here and I'm going to the left, as x gets really, really big, as x goes towards infinity, what is happening to your y values? And what's happening here is our y values are going towards positive infinity. If I look at the other direction of this, and now I take a look at what's happening as x gets really small and as x goes towards negative infinity, well, notice that what's happening here is that your y values are still increasing, and those y values are going to keep going, and so our y values here are also going to be going towards positive infinity. So in the end, everything here is increasing. If I look at this graph here, okay, this is like the cubic function. As I look at x, as x increases, what's happening to your value of y? Well, now your y value is increasing as well, just like we saw before. So as x goes towards positive infinity, y is also going towards positive infinity. If I look at the next one here, where I want to look at x going towards negative infinity, well, now I have my y values going in the opposite direction. Now we're going towards negative infinity. And so as x goes towards negative infinity, y goes towards negative infinity. It's going down to the bottom left corner of your graph. So sometimes you have them approaching to infinity because they're going to be continuous and they're going to go on forever. And then sometimes you're going to have them approaching asymptotes. Now this graph right here, if you can kind of look real carefully, you'll see that both the graphs on the left and the right hand side, they're kind of reaching a plateau. And they're reaching a point here of that I could put in a horizontal asymptote at positive 3. So as I look at my graph and I'm looking at, well, what's happening as x goes towards positive infinity? Well, my y value is increasing, but then all of a sudden it kind of reaches a maximum point. And so as x goes towards positive infinity, my y value is actually going just towards positive 3. And that's where it's going to end up stopping. If I do the same thing with the other graph here, and I'm going in the opposite direction as x goes towards negative infinity, I'm going to see the exact same thing where our value of y is going to be going towards positive 3 as well. They're going towards that horizontal asymptote. With my last graph that I want to look at here, you'll kind of see how it's kind of crazy, a little interesting little curve to it. And, I don't care about the maximums and minimums. That doesn't bother me. What I want to know is what is happening as x gets really big or as x gets really small. Now, as x gets really large here, what I see is that my graph, as it started to increase, well, then it started to decrease again, and now it's starting to kind of plateau once again at the value of 0. And so here we have, as x is going towards positive infinity, our y value is actually going towards 0. As I look at the other side of this, and I look as x gets really small, my graph from here, if I look at where it's going, we'll see that it's plateauing once again. It started out at 0 and then it came back But if I go from the origin, I look at what's happening over time, here we are also going to 0. And so as x goes towards negative infinity, y is also going to approach 0. So in a couple days, we will be going over what's called the limit notation for this. But right now, I just want you to be looking at what's happening overall with the end behavior. So there's a lot of different things that we covered here today. So if you have any questions on anything, make sure that you write it down and you come to me with any questions that you may have.